Hi everyone, and welcome back to 14.4. We're going to look at flaws of the apportionment methods. So just like there were flaws in the voting methods that we looked at, we discussed apportionment methods in 14.3, which was how to fairly divide up things. And we're going to focus on one of the flaws of those voting methods. Or apportionment methods. We're gonna specifically look at Hamilton's apportion method, and three flaws or paradoxes that occur with Hamilton's method. Now, remember that the apportionment method should satisfy the quota rule, and Hamilton's method was one of the ones that did satisfy the quota rule, which said that an apportionment for every group under consideration should always be either the upper quota or the lower quota. But you're going to see that there are three different paradoxes that occur with Hamilton's method. One of them is called the Alabama paradox. The other is the population paradox, and the new states paradox is the third one. And the Hamilton's apportionment method, is not so perfect. So the Alabama paradox occurs when an increase in the total number of items to be apportioned results in a loss of an item for a group. Let's take a look at an example. And please feel free to pause the video so you can read the problem, as many times as you need to understand what's going on, and then we'll discuss. So consider a small country with a population of 18,000 people and 3 states. We'll call them A, B, and C. There are 150 seats in the legislature that must be apportioned among the 3 states according to their population. So we want to show that the Alabama paradox occurs if the number of seats is increased to 151. And we're going to round standard divisors and standard quotas. Again, since we're dealing with Hamilton's method, right? We're dealing with standard. We're going to round those to the nearest hundredth. So we know from 14.3, first we're going to take our total population, which is 18,000, and divide it up by the number of seats, which is 150. And this is giving us our standard divisor, right? Which will end up being 120. So then what we would do is to get our standard quotas for each state, we would take 888 divided by 120, 8,076 divided by 120, and 9,036 divided by 120. So we're going to make a little chart here. Okay, so we've got our state, we have our population, the standard quota. Okay, so we're going to get that from the standard divisor. We're going to look at the lower quota, and then Hamilton's apportionment. So our states are A, B, C, and then we have a column for total. Okay, and we know that our population, I'm just copying from the chart above. Okay, when I take 888 and divide it by, dividing by, 1 second. Okay. Divided by. Yep. Okay, so we've got our 888 divided by 120. Just wanted to double check. That comes out to 7.40. 8,076 divided by 120 is 67.30. And then 9,036 divided by 120 comes out to 75.30. Okay, so lower quota, we're going to round down, right? So which is what we do for Hamilton. And if we add up those numbers, we end up with 149, but if you'll recall, there's 150 seats in the legislature. So remember what we did was there's one extra seat, and that would go to the state that has the highest fraction, which would be 0.40 compared to 0.30, so 0.40 is higher. So we're going to add one more seat to state A. So they would have 8, that would stay 67, that would stay 75, and now we've got 150. But in the video, or in the problem, we are increasing the seats to 151, okay? So now when that happens, when we increase the seats to 151, our standard divisor is going to change, right? It's going to be 18,000 divided by 151, which is not going to go in so perfectly. It's 119.21. So now we're going to create a new table, and this time we're going to take our population and divide it by 119.21. Okay, so I'm going to actually just copy and paste this chart and erase some things. So this is for our new table, and I'm going to get rid of these rows here. Okay, so let's see what happens. So now I'm going to take the populations, I'm going to divide by 119.21. So when I do that, I get the following. And that's 75.80. Okay, so we're still dealing with our lower quota, which is 7, 67, 75. And if you add that up, let's see, 7 and 67 is 74. 74 and 75 gives us 149. Okay, so in Hamilton's apportionment, this is going to stay 7. And actually, when we add those, let's see, 67 and 7 is, yeah, so there's actually 2 that are empty, right? Because if you add 7, 67, and 75, you get 149. And we need our total to be 151 now. So if we look at our decimals, the highest ones would be these 2. So using Hamilton's method, those would be the 2 that we would add 1 more seat to. So now that's going to add up to 151. But as you can see here, State A had 8 seats and they just lost 1. Okay, so that's what's called the Alabama paradox. And again, that's when an increase in the total number of items to be apportioned results in a loss of an item for a group. So State A lost a seat because they increased the number of seats to 151. Okay, let's take a look at the population paradox next. The population paradox occurs when Group A loses items to Group B, even though Group A's population increased at a faster rate than Group B's. Okay, so this has to deal with like the rate of increase or decrease. This is another paradox, and it occurs, again, all of these paradoxes occur within Hamilton's method. Okay, they can occur. Consider a small country with a population of 100,000 and 3 states, A, B, and C. There are 100 seats in the legislature that must be apportioned among the 3 states. Using Hamilton's method, we already have the apportionment shown in the table. Okay, so that's after doing all the work. So let's just say the following. Suppose the population for each state increases. Okay, let's say that state A now has 23,926 people. State B now has 5,648 people. State C has 71,110 people. And let's say the total is 100,684. Okay, and we'll keep the number of seats to be apportioned the same. So we're still dealing with 100 seats. So what I want to do is I want to calculate the percent increase. Okay, how much did each of those states increase? By what percentage? Okay, so to calculate percent increase, what you're going to do is you're going to take the new total, which let's look at state A for instance. The new total, which would be 23,926, you're going to subtract the old population total, which was 23,527, and then we're going to divide by the old, so the original. It's kind of like a percent increase problem when you're dealing with prices. It's always the new price minus the old price divided by the old price. So same thing, except we're dealing with population. Here, you would end up with let me show you. So you're going to get 23,926, and then we're going to subtract 23,527. Okay, and that gives us 399. So we know there was an increase in 399 people in state A. And we're going to divide by the original, which was 23,527. And we get 0.016959, etc. So I want to change that to a percentage. So what I'm going to do is multiply by 100, or just move the decimal 2 places to the right. So if I move the decimal 2 places to the right, I'm going to end up with 1.696. Okay, so basically, 1.7% increase. Okay, I'm going to do the same thing for B, except I won't work out the formula for it. It's just going to be the old total, or the new total rather, so 5648 minus the old 5548, and then divided by the old 5548, and you end up with 1.802%. And then for state C, you're going to take the new one, 71,110, subtract the old, and then divide by the old, and you end up with 0.261%. So if you're looking at the states and you want to know which one increased at the fastest rate, it would be B, because it increased at 1.802%. Okay, so let's make a table and let's see what happens. So before we make the table, let's figure out the new standard divisor. So we know we have our new total is 100,684, and we've got 100 seats. So we're going to divide by 100, and we know that's just going to give us 1006.84. Okay, so that's our standard quota. And now we're going to use that to fill out our chart. So we've got state A, B, C, and then we'll have a column for total. And then we're going to have our standard quota And since we're dealing with Hamilton, we're going to have our lower quota and then Hamilton's apportionment in the last row. Okay, so if I take the population and I divide, so I'm going to take the new population, 23,926, and I'm going to divide by 1006.84, and then do that for all of the states. So you're going to divide these each by the new standard divisor. Okay, you're going to get the following for your standard quota. And then remember, we're always rounding down for Hamilton. Okay, if I add those up, you get 23 plus 5 is 28, plus 70 is 98. So there's 2 seats, and we want to figure out which 2 get it. So remember, we look at the fractional part. 0.76, 0.61, and 0.63. So the highest ones get the extra. So state A and state B have the highest fractional part. So we're just going to add 1 to each of those. So state A would now have 24, state B stays 5, and state C is 71. And then when you add that up, you get 100. Okay, what do you notice happened? Okay, so state B actually lost a seat. When they had the smaller population, they were apportioned 6 seats. But now, when the population increased, they lost a seat. So that's where the population paradox occurs. Okay, because state B had the fastest increase in the population. So you would think that they would either maintain the number of seats apportioned or they would, gain more. But even though their population increased at the fastest rate, they lost a seat. Okay, and that's the population paradox. Okay, the last paradox we're going to talk about, again, and it refers to Hamilton's method for apportionment. It's called the new states paradox. And this paradox occurs when the addition of a new group and additional items to be apportioned reduces the previous apportionment of another group. Here's an example. The Florida Public Library System has received a grant to purchase 100 laptop computers to be distributed between 2 libraries, A and B. The 100 laptops will be apportioned based on the population served by each library. The apportionment using Hamilton's method is shown in the table. Okay, so we have our standard divisor, of course. It's 10,000, which is the total population, divided by the 100 laptops. So our standard divisor is 100. Okay, here's a scenario. So suppose an anonymous donor decides to donate money to purchase 6 more laptops. But there's a condition. The third library, which is library C, okay, has to be included in this apportionment. Okay, so library C must be included, and they have a population of 625. Okay, so what we're dealing with now is, you think about like the apportionment table, what things change. So because of this donation, they're getting 6 more laptops, but they have to include an extra library, which would be library C. So now the total is no longer 10,000. The new total would be 10,000 plus 625. So our new total, new population total, would have to be 10,625. Okay, and it's no longer 100 laptops, it's 100 plus 6. So now my standard divisor will be different, right? My standard divisor is now going to be my new total divided by the total number of new laptops, which is 106. So 10,625 divided by 106 comes out to 100.24. Okay, that's my new standard divisor. Okay, so when I'm making my table, I'm going to now divide the populations each by 100.24. Okay, so this time I'm dealing with libraries, and it's library A, B, and C, and then a column for total. And then of course we're gonna have we'll put a population row. We'll have our standard quota. Since we're dealing with Hamilton, it's gonna be the lower quota, and then we'll do Hamilton's apportionment. Okay. So the population of library A is 2145. B is 7855, and I'm just getting that from the table above. Now we have to include C, which we said is 625, and our total is 106.25. And we know our standard divisor is 100.24, so we're going to divide the population by the standard divisor, and you would get these numbers. Okay, and then we know we're going to round down. If I add that up, I get 105, so we're missing 1. So we would want to look at our fractional part, and the one with the highest would be state A. So they get 1 additional 1. So they would have 22. B would stay 78. C would stay 6. And now we have our 106. Okay. So if you compare this chart with the one above, what do you notice happened? Okay, not only should you see that state A gained 1, more importantly, state B lost a laptop. So they were apportioned 79, and now they have 78. Okay, and this is called the new states paradox. So library B ended up losing a laptop. So that leads us to some summary points that Hamilton's method, as we can see, produces paradox. Now, that doesn't mean Jefferson's, Adams, and Webster's methods don't. They can all violate the quota rule, okay, but they don't produce paradoxes. So only Hamilton's method can produce paradoxes. Jefferson's, Adams, Webster's methods can all violate the quota rule, right? Hamilton's method does not violate the quota rule, but those three do, okay, and that's important. Because remember, they shouldn't, to be fair. Hamilton's and Jefferson's apportionment methods can favor large states, whereas Adams and Webster's apportionment methods can favor small states. Okay, and there is what's called Belinsky and Young's impossibility theorem, and it states that there is no perfect apportionment method that satisfies the quota rule and avoids all known paradoxes. Okay, so just as there was no perfect voting method, we saw that there were flaws in each one. There's no perfect apportionment method either, because even though Hamilton's doesn't violate the quota rule, there's paradoxes. And then the other three violate the quota rule. So there is no perfect apportionment method that satisfies both. To finish off this section, if you could kind of summarize here the apportionment methods and the different rules, whether it satisfies the quota rule or whether it violates and has one of the paradoxes. So if you would fill in the table with yeses or nos, and you can pause the video and try filling it in, and of course refer back to your notes if you need to, and then unpause it when you're ready to check. Okay, so we know that Hamilton's does not violate the quota rule. It's the only one that doesn't. The other three apportionment methods do, okay? But Hamilton's then has the paradoxes. So Hamilton can have any of these three paradoxes. And we said that Hamilton's can favor a large apportionment. And that also goes for Jefferson. Okay, they both favor large states. And then these are all no, because Jefferson, Adams, and Webster don't have any paradoxes, but they do not satisfy the quota rule, whereas Hamilton's does. And Adams and Webster favor smaller states. And that's it for 14.4. I hope you've enjoyed this chapter and learning about different ways to vote and different ways to apportion, and then also that there are flaws with all of the methods, both voting and apportionment.